Okay, so it's a pleasure to welcome all of you in those who are joining us in the Zoom platform. And I know people are still joining in, as I can see from the participant list. And those who are joining in from our YouTube channel, I welcome all of you for this edition of the Wednesday Colloquium. We are back after a month, and we are opening this 2021-22 series with Professor C. Malla Reddy from Indian Institute of Science, Education and Research, which is IISER, in Kolkata, West Bengal. Before I actually introduce our speaker today, I would like to give a brief background of the Wednesday Colloquium. So the Wednesday Colloquium, as instituted by Professor Homi Bhabha, our founding director, is a scientific forum which is as old as TIFR itself. And it was his idea and vision that all the scientists working at TIFR, whether be a physicist, chemist, or biologist, get together once a week at 4 o'clock on a Wednesday afternoon and listen to internationally well-known experts talking about contemporary research questions and ideas and breakthroughs. Today, of course, is no different. We have Professor Malla Reddy, who is pioneering a field which is at its nascent stage, which is looking at flexible crystals that could be bended. So before I give Malla the floor and let him discuss this idea, I would just give a brief introduction. So Professor Malla Reddy is actually the head of the Department of Chemical Sciences at IISER, Kolkata. His work actually focuses in sort of interdisciplinary areas, but mostly in applied crystal engineering. Okay, his group is, as I said, is pioneering work on mechanically flexible molecular crystals, their structure-mechanical property relationship, and also very recently, with a publication in Science, they have shown that they can also look at self-healing single crystals. Of course, with this kind of fantastic work that is going on in his lab, we'll all be interested, where did he get his training from? His PhD work was in University of Hyderabad with Professor Gautam Desiraju and with Professor Padmanabhan as a co-PI. After doing some very interesting work with Professor Desiraju, where he looked at bending of crystals, he went to postdoc at Institute of Nanotechnology at Karlsruhe Institute of Technology, KIT, in Germany, where he spent almost a year. After taking up that position, he actually sort of was a visiting scientist at various times at KIT, but joined sometime in 2009, Malla, right? 2009 in IISER, Kolkata?
2008
in IISER, Kolkata. And he has been there ever since. Of course, because of his fantastic work, Dr. Reddy has been awarded the Swarna Jayanti Fellowship, which he received in 2015 from the Department of Science and Technology. He has, of course, been, been associated with various journals. Primarily, he's been an associate editor for Crystal Engineering Communication by RSC and Acta Crystallographica Section B. One of the most important parts of Malla's research has been to sort of make crystallography or advertise crystallography in various forms, and he has been sort of one of the important members of the organizing committee of the International Union of Crystallography meeting, General Assembly, which was last held in 2017 in India, and he was one of the important members organizing that. Without any further any delay, I would now request Malla to talk about his work, which he has titled "Crystal Engineering of Adaptive Smart Materials from Mechanical Bending to Self-Healing." Malla?
Yeah, thank you very much, Jyotishman, for the nice introduction and for the invitation. last time when I visited, so I really thoroughly enjoyed the stay there and then interacted with all of you. And many friends are in the audience. I can see them. So we have some updates, like what I presented last time. So I'm going to still present some of those results, and then I go into the recent results that we have. We have actually made progress in recent times. So with this, thank you again for inviting me. It's always a pleasure to interact with and then face the very tough audience here. So uh, s- uh, yeah, first of all, let me thank all my students and then former students and group members and all my collaborators. So I'm going to present work from various people with whom I have collaborated, and I still collaborate with some of them. And then funding agencies, definitely DST, SERB, and CSIR, and CIPLA also. In recent times, I've been working with them as a consultant, and then the funding is really very helpful for our group and some of the to support our students and IISER Kolkata. And I also thank IISC's this Sensei. This is Center for Nanoscience and Engineering, where we have done some high-end experiments, and it was really helpful. Although we paid, but it was really good to have it in the country. So that helped us to do many things within India for our some of our to understand some of our problems. Then finally, Christinchcom, where I work with them as an associate editor, and after Christ B, I'm a co-editor for that. I also thank them for for giving me an opportunity to work with them. So although I have named some of them already, many other students. So I'm going to present the work on the self-healing crystals, and these are the people mainly involved in that work. And so it was really nice. And so it was, since it was a complex problem, we had to understand this from different angles, and we needed expertise from different people. So some of these people were here. So from physics department, my colleague Professor Nirmal Ghosh, and his students Shubham and other students, and my own students, rest of the students. So I thank all of them. And although I am presenting some of these results here, so they are the ones we have done. So I thank all of them. So before going into the details of my talk, I would like to just give you a brief overview of what I'm going to basically cover today. Uh, I'm going to basically introduce you to the mechanically responsive organic crystals. Then I just quickly show what we have done and what other people have done in the field, and where exactly the field is going right now. So I think this should give you some idea about the crystal engineering and then mechanically responsive crystals that very recently have come up, and these are very, very interesting. And so these some of the things that we see here have a strong overlap with the soft matter. And so people have invested a lot of time in soft matter, and the field is really at an advanced stage. But when it comes to the organic crystals, so it is still in a very early stage. So we still don't understand many things, and some of the things that we study probably can be explained by the things that are known in the soft matter. So I'm going to just show you some examples. Then I go to mechanically bendable crystals, plastic and elastic crystals. And then at the last part, almost at the middle of my talk, I'm going to basically go into the self-healing molecular crystals. And then I show you the challenges to study self-healing crystals, and then some of the insights that we got into the mechanism and some of the broader questions that we have. So this is what I'm going to basically cover in my talk. So as crystallographers, we always wanted to have very good crystals. So nobody wanted to deal with the bad crystals. So everybody only wanted very good crystals, and anything that was not meeting the criteria, if you don't have a very good diffraction pattern, and you just throw it off. So that is what people have been doing for almost 100 years, like since the crystallography came into existence. So if your crystals are not good, obviously you don't get a very good structure, because the diffraction would not be good, and then you will have to really work hard to solve the structure. If it are you're lucky, you will get the structure, otherwise you don't get. So that's why most of the people wanted only good crystals. So anything that was not looking clean and shiny is totally unwanted. So that's what people have been basically doing in crystallography. So we have now a large number of crystal structures in the crystal structure database, and now crystallography is really flourishing with a large number of structures. And so but now I think because of the advancement in the techniques, and now we can really go into very small micrometer scale or even nanometer scale and then probe the structures. So there are a lot of there is a lot of advancement in the tools that we have. So this gave an opportunity to the people working in the area to look at the crystals which are not really very good. That means they are not very robust, like very, very soft crystals. So for example, if you have something like this, if you are a crystallographer, if you are interested only in the crystal structure solution, normally you don't basically take crystals like this. But most crystallographers have seen crystals like this, and these were known, and soft crystals were known to people, but nobody really paid any attention to look at what exactly is going on. Everybody wanted a crystal something like this, but nobody wanted a crystal something like that. So now these are now known as soft crystals. And so when I was doing PhD, actually, we were working on halogen bonds, and then I basically made some halogen bonded compounds which were interesting for the halogen bonding interactions and all. So then when I was looking at those, I actually, as a PhD student, found some crystals which could be easily bent. Then it was very surprised. I was very shocked to see these in the beginning. Then when I went to Professor Gautam Deshiraju. He was also very much excited. But we couldn't do much because we could not diffract, we could not do a lot of things. So then, but still we tried to understand what exactly was going on. So this work in those days we published in Chemical Communications. And so if you look at, actually, we try to understand what is going on here. So initially we got one or two examples. Then later we did a survey, and then we got about 10 different crystals, totally different compounds with exactly the same bending property. So then what I did is I looked at the crystal structures and then found that all these crystals have weak interactions. So these are more or less like van der Waals interactions, and then you have stacked columns most of the time, and within these columns you have relatively stronger interactions, and between the columns you have relatively weaker interactions. So because of this, so the crystals could be easily, like these layers in the molecule, the crystals could easily slide one over the other, and then that would basically lead to these bending deflection. So when you,
Sorry to interrupt.
yeah,
I just want to know, did you say that you could not get diffraction from this?
we could get the diffraction from these crystals, but this was not good enough to solve the crystal structure. So that was a problem. And because the peaks were broadened most of the time, and you could not basically solve the structures from those. But now we can do it. If you have a very small X-ray beam, then you have very less overlapping. So you have to go to synchrotron. That we have done now, but in those days, we did not even understand what exactly was going on, and we didn't know what techniques would be helpful in those days.
So
So
under what basis do you call them a crystal? I mean, I guess I'm getting a little
see,
maybe pedantic here,
definitely,
but
yes,
the idea of when is something a crystal and when is something not a crystal?
yes, Deepa. So here, if you look at, for example, so this was a crystal. Okay, this was a single crystal, and you could diffract it beautifully, and you could get a structure. So when you apply mechanical stress and then you bend it into the shape like that, okay, so then it's a good question whether you still call it a crystal or not. So the definition normally says that anything that gives you a diffraction pattern with X-ray, or for example, is you can broadly call it a crystal. Whether you call it a single crystal or polycrystal is still debatable. Uh, but if you are looking at from the crystal structure point of view, and it is a tool that is more important. If you have a very broad peak, like the beam, very wide beam, and you overlap basically because you're collecting the data from different regions, and the orientation of the packing is different in different regions because you have something like that. The structure is something like this now. So there would be overlap, but if you take a very small beam and a very intense beam, you will now get a very good diffraction pattern. and then with some kind of a,
Agree. So I guess it's the domain size is what I'm trying to get at. So, when you say it's a polycrystal is still consisting of crystalline domains.
Exactly. Yeah. So that is where, you have smaller domains. So then if your beam is small, then you will be able to get meaningful diffraction pattern, and that will allow you to solve.
So as long as you get a meaningful diffraction pattern, you're saying that you calling it a crystal then.
Yes. Yes. It is still
so
a
it's
crystal.
instrument based. I mean, what was being called a crystal, let's say 50 years ago, or not being called a crystal 50 years ago, can be called a crystal now because of instrumentation.
No, even in those days, you would still call a crystal because you still get a diffraction pattern. But when you want to solve a structure, you don't, as a crystallographer, you don't want to call it a crystal. So it's like,
All right.
if you go if you just go with a vague thing, but if you go into the details, like then domain size and then the probe, everything comes into the picture. Yeah.
Okay, can I just interject?
Sorry.
Yeah, no, that's okay. That's okay. Can I just interject from a standpoint of a question? As Deepa asked, Malla, and I think your discussion for everybody in the audience was also important. I just wanted to ask if you do not see a diffraction pattern at a length scale of a probing beam that you're using to get the diffraction pattern out, is that something not been thought about for all these years? Because people have been the mere definition of single crystal should involve the facets should be all well defined in such a way that everything should be properly oriented, right? And when you have a polycrystalline samples, those facets are not in the right orientation for the entirety of the beam to go through, and you get the very clean spots. Now,
yes.
That also was a length scale argument, right?
Yes,
so the
yes.
probing beam and the length scale of the entire crystal should both be important. And since you bend it out, if I probe it at the bent region, would I see a diffraction pattern which is reminiscent of a single crystal, or would I see a diffraction pattern only which might be composing of multiple polycrystalline parts?
Yes. So let me make one thing clear. So we are basically like debating between the single crystal and then crystal. If you just want some call something a crystal, that includes both polycrystal and single crystal, polycrystalline material and single crystalline material. Where you call something a crystal when it is a monolith, okay? Then you divide it into single crystal and then polycrystal, basically. Okay. So once you bend it, it is more like a polycrystal. So, but still, whether the polycrystalline one, do you want to call it a crystal or not? So then you need to look at the domain size and then local order, and it should have reasonably good long range order so that you can get a diffraction. So that is the context. That
okay, thank you.
Yes. So basically, then we propose this model here that these basically you have a slip plane, and then molecules basically would move using these weak interaction planes, and that is how these become soft. So we propose that based on several examples, and then that was sometime in 2005. And then after I joined in IISER Kolkata, so we again started working on mechanical properties, because at that time not many people knew about this and nobody had expertise to work on it. So we were working on mechanical properties, and then we encountered elastic crystals. So here it is plastic. Once you bend it, it doesn't come back. But here, this is an elastic crystal. Once you bend it, you can bend it into a loop. Then when you release the stress, again, it comes back. It springs back. So this is called elastic crystal. So then again, people probably have seen, and even when you look at the old papers, the TEMs and all these fiber-like crystals were always like bent, but nobody really paid an attention to understand from them from the mechanical property point of view. And so we got into the details, and then we basically tried to understand why this is an elastic crystal. And so then we studied, and then we basically explained why it is elastic. And so I'm not going into the details of that. And then we basically kind of explained the difference between the plastic crystals and plastically bendable crystal and elastically bendable crystal. So for example, if you have a crystal, if you look at this this angle here, so if you bend an elastic crystal, so more or less you have a compression here, and then you have a tensile stress here. So you are basically pulling apart the molecule cells here, unit cells, and then you are compressing the unit cells here. And then you have a uniform kind of a, not uniform, but it's a kind of a distribution of the stress here. And then stress is not released in the case of elastic crystals. And then you don't see a big change in the interfacial angles at the tip of the crystal. But when you go to the plastic crystals, since there is a slip here, and once you have a slip, stress is more or less released. And so that is why you have a change at the interfacial angles. And that is what we found in most of these plastically bendable crystals, as you can see here. So, so this allowed us to explain the difference. And then since the stress is released here, so it doesn't spring back, and you have weak interaction planes here. But in this case, molecules cannot slip. So that is why these are elastic. So that is what we proposed.
Malla, sorry to interrupt again. Just to clarify, are you saying everything remains the same and just the unit cell is compressed, means the point room its symmetry remain the same? I mean, I'm having a hard time understanding this compressed unit cell from
yes, Deepa. So see that although at the macroscopic scale it looks enormous, the changes, but when you go to the microscopic scale, like at the unit cell length, these changes are something like 1% or 1.5%. So when you get the data from the single crystal XRD, for example, using these very fine microfocus.
So these are similar to sort of like a piezoelectric response?
It's not a piezoelectric. It's kind of, the deformation that you see is similar, but these need not to be piezoelectric. They need not to be basically like polar crystals. Okay, so yeah. So
no other property of the material changes other than the unit cell compression? Are you sort of suggesting?
No, I'm not suggesting that. A lot of things change. Whether you still call this a crystal, that is still a question. Do you still call it a unit cell? See, it all depends on the length scale. What is your tolerance? For example, if you look at unit cells here and here, they are different. Do you call them as different phases? And they are different. So there is a basically kind of a uniform change. It's you have a constant kind of a function, basically, like you from here, if you go to the tip, it is more or less comparable to the single crystal, normal crystal. And then when you go closer to this point, then you have more stress, then again gradually it decreases. So it is a kind of a function that you have, and it is not random. So it is all distributed kind of a gradient. There is a gradient. So then when you go from this side to this side, again, this is kind of a neutral point, neutral axis, where you don't have much change. And when you go here, there is a expansion, and then here there is a compression. The compression and expansion is along this direction. Okay, then in other directions you may have different response. So these changes are very small, but theoretically, if you speak, these are all like deformed unit cells. Okay, but the properties change. If you look at inside and outside, the properties are different. People have shown recently that properties, for example, fluorescence properties. There is a small change. Change is small. I don't know whether you call these as different phases because they are not stable. Once you release the stress, then they go back. Basically, you are straining the cell. So you would still call them, because they are not in a local domain or local stable. You are putting them under pressure. So
is it a necessary criteria that all these crystals have one direction very different from the other direction?
You mean the length?
No, the properties are very anisotropic. That's all that I meant.
You mean this
because
outer to inner?
Yeah, in any direction. I mean, because you kind of the pictures that you're drawing, and also because in mechanics is the estimation cost problem, but it's like if I held papers, if I held a bunch of papers and then tried to bend it, and if I held them together and I tried to bend it, and it will kind of laminate out from each other. But you're showing it a very nice thing. You're saying that I held the two ends free and then I actually bend it out, and hence I don't see this. The stress is released at every layer. But when you say the stress is released at every layer, it kind of gives me a feeling that as if that these are very anisotropic objects. So
these are anisotropic. These are anisotropic. The stress distribution is also very anisotropic. And so if you basically go a little more than the elastic limit, so you will see lamination. You will see the cracks here, and then sometimes there is a bulge here because we are too much, compressing them. So you see all those changes basically. Yeah, this is a stress distribution is also anisotropic here, but since you have a slip here, so the stress is somewhat less in the crystal here. So because but your order is somewhat less in this case, but here it retains the local order at least, if not the long range order.
Thank you.
Okay.
One interruption, sorry.
Yes.
Yeah, I have known bent crystal spectrometers for a very long time. These are used in X-ray spectroscopy, X-rays and gamma rays, and they actually have bent crystals. So I'm missing something here. Why is this such a big, thing that you're now able to bend crystals? Because these crystals in spectrometers have been used for a long time in the 90s and even earlier probably.
Exactly. Yes. So they were used. I think most of those were inorganic crystals. I think they were put under stress and then bent, and then you use them to basically for aligning the beams, or sometimes even to
directing the diffracted beams.
Exactly. Yeah. So here, you see, these were also known. People knew that the crystals would bend. Yeah. But then the question is, which crystal would bend, which crystal would not bend, and how much they will bend, and what is the mechanism? When you bend, what exactly happens? Do you see any change in the properties?
Yeah.
So these are the questions that we are trying to address. Can you design them? That is the ultimate goal.
You're saying that organic crystals may be softer than the inorganic ones. So can you shape them the way you want? Is that the broad goal?
I think I will show a lot of examples. You would see that crystals. Probably you will forget all the brittle crystals. So, okay. I will take you through some of those examples.
There's one more question by Indranil. There's one more question.
Hello, I have just a quick question. If you are talking of the properties, so once you have bent these crystals or polycrystals, whatever, are there changes in the optical properties? Like if it is a scintillation material, let us say, will there be a change in its properties, or do we know any specific example?
So so basically, like fluorescent properties have been studied, and people have shown that if you bend the crystal, outer side and inner side, you have different stress. Here it is a tensile force that you apply, and then here compressive stress, right? So then people have shown that the optical properties are slightly different here. So there is a shift in the peak, in the optical properties. That is what people have shown, but not much is done in terms of other properties. It's very new, so people are now trying to understand different things.
Any knowledge about this quantum efficiency of conversion? I mean, if a radiation is absorbed, that how much visible photons are produced? Is there any change possibility, or it is only in terms of the transportation of the photons inside?
I think there would be changes definitely, but the question is how much the change is, whether you will be able to observe it or not. But then different materials can go to different levels of stress. So there are some crystals, especially the thinner ones, they can go up to 10%. But if you go to the inorganic materials, normally like 1% is already quite high. But here you can go to 10%, sometimes even more. So that gives you an opportunity to, see these changes in terms of some technique, using a technique or something.
Okay. Can I sorry, Malla, we are keeping you on the slide. Just one last question, because you have shown a bending of the crystal, but you've not really compared the length scale of the bending to the actual lattice parameter. So when you are showing this bending, you are bending a crystal which is micron size, correct? Yes. Is that correct? And yes. How much bend angle can you create, and how much does that translate to an absolute change in the lattice parameter for the ones that are on the outside?
Exactly. In the lattice parameter, for example, you take the unit cells. It is like about 1 to 2%, 3% sometimes.
Oh, that's a very small number at the yes. lattice parameter, but that is a sufficiently.
Exactly. That is sufficient enough to see property changes.
Okay.
But it is again, it's not big enough to break the whole thing.
So 1 to 2% you mentioned, which means if the lattice parameter is an angstrom or 2 angstroms or something like that, or maybe 3 angstroms, I don't know. So that would correspond to picometer changes, few picometer changes.
Yes.
Right?
At the molecular level, these changes are quite small. Yes. If you look at from the in terms of percentages.
Right. And that is sufficient for also building charges in polar crystals or something else. Like
exactly.
Okay.
Yes.
Okay. Fine.
That's true.
Thanks.
Yeah. Okay. So this is the difference between elastic and plastic crystals. And then I would like to show some videos for the brittle ones. Most of the crystals, 90% of the crystals are brittle. So when you try to apply stress, so they simply break. And then, as I said, these are elastic crystals. So then when you bend these crystals, so they bend, and then when you release the stress, they basically spring back. And as you can see, this is a first example from our group where we studied in detail and then tried to correlate with the structure. Although we didn't get everything right here, mechanism part was what we thought was not exactly the same. But then people came up with more detailed, X-ray crystallography studies and all. They have shown. I'm going to show a slide on that. And then these are the plastically bendable ones where you have this slip. Okay, so here they don't come back once this is a plastic deformation, so it is not reversible. You can push it back, but you don't get the same quality, same crystallinity here. So you have a lot of defects in this case, and it is a permanent one. So then again, we try to understand whether the model that we proposed, the slip plane model, whether that was right or not, using some advanced techniques. I'm not going into the details again. So this was the mechanism that we proposed for the plastically bendable crystals. You have weak interaction planes, and then you have stacks of molecules. So then because of this slip, then you have the bending. So then again, we try to do nano indentation. We have done the diffraction studies using the synchrotron, microfocus synchrotron, and we see that there is not a big change in the lattice parameters. There is some change, but it's not a big change. And more or less, it confirms that the model that we proposed is somewhat, in general terms, it follows, and that is what we proposed using synchrotron studies here. So then when you come to the elastic bending, so a group from Australia, Jack Legg and McMurtry, they have looked at this copper acac, so copper acetylestonate crystals. So this copper acac crystals, basically, if you take a crystal and then you can basically bend it and you can make a loop out of it. And so here, if you look at, this is the packing. If you look at along the needle direction, this is a bent crystal. They have done the they have basically done the diffraction studies here. You can see the diffraction. This is a crystal mounted on the loop on a diffractometer, and then you make a loop. This is a bluish one, is the crystal, and then you diffract. So they have basically moved the diffraction spot very little, and then collected a lot of spots across this, along this line here, along this axis, and then they got the crystal structures at each point, and then they saw that on the outer side you have a elongation along this direction, needle direction, and then there is a compression along this same needle direction. So here you are compressing the layers, and that is what we said. This is a very well-known elasticity theory, right? So on the outer side you always elongate, and then on the inner side you have a compressive stress. So what is important here is you see the mechanism here. So here these molecules, which are kind of a corrugated, so the angle between these basically decreases here, but here the angle basically increases. So when you push them, so they are becoming more or less flat when you put them across, compared to this axis, and here they are turning away from the axis, this axis. So this allows you to increase the length in this direction and decrease the length in this direction. So that is the inner side, and this is the outer side. You can see it here. So when you move the diffraction peak from this, spot from this side to this side, and then collect the data, and then as you come inside, and then this axis basically increases, axis in this direction basically decreases. So these are the small changes that you see when you basically bend these. So of course here the bending that they have done is very, very small, and the percentage of strain they could get in this particular crystal is around 1%. But there are other crystals which can go up to 10%. So in those cases, if the mechanism is exactly like this, so then you would see much larger changes. But this shall give us some idea about the bending mechanism. So this was done by the Australian group, and then they have again compared the changes in the unit cell and then plotted all these, and then showed that the different axes basically change, like unit cell parameters change, but volume more or less remains. So this is the volume. So that volume more or less remains same. Okay, so that is what they could see in this. But this is just one example, and there are not many studies. It's not very easy to access synchrotron for for a lot of people. So still the number of studies are very less. and this is what they have proposed. And this may be seen in many other crystals, but there could be other mechanisms as well. So because all the crystals don't pack similar to this, there are different types of packings. So that is why there could be different ways through which you could achieve the elasticity in crystals. And so then several groups have actually started working on elastic crystals, and then Japanese group have shown fluorescence in a elastically bendable crystal, and then they have even studied the photophysical properties. And then I'm not covering here, but they have shown the difference in the emission peak on the inner side and outer side. And then this is the coordination complex, and even metal organic complexes also show the elastic bending. And here again, this is a metal complex, and here it is a plastically bendable plastic bending, what you see here. And here you could even twist the crystals. So this is again Chinese group. So they have shown that you can actually twist the crystals, and then when you bend, it is elastic, but the twisting is plastic. So twisting is irreversible, but bending is basically reversible. Then there are crystals which also jump, because when you have a phase transformation, and unit cell basically changes very quickly, and then that changes shape of the material very quickly, and then that basically leads to this thermosilent effect. And then again, heating also can basically split the crystals, and then you can see a lot of dynamic effects in the crystals. And so this is a super elastic crystal. When you heat it, when you push it basically from the top, you see a phase transformation, or sometimes it is just a twinning, or sometimes it is a phase transformation. So you have two different domains, and this domain basically when you push it, so this comes and then goes away again. When you release it, it goes back. And so here, this is a phase transformation. I think this is a twinning. I don't remember exactly, but there are different things in different examples. Either it could be twinning or it could be a phase transformation. In this case, it is a clear phase transformation. As you can see here, the emission color actually changes here. So this is yellow green, other one is yellow orange. So you can basically do it in a reversible manner, and you have different phases. So you are changing the phase by applying mechanical stress here. So this was again shown by the Japanese group.
Just a small question, can I?
Yes, please.
Yeah, these are observational mostly. Meaning that how sophisticated are these measurements? Because they all seem to be very high profile papers. So what makes it, what is the challenge in making these observations, or is it, where is the challenge?
Okay, so basically, like, here observations were not made in organic crystals. I know there are other materials, people knew these for a long time. But observations in organic crystals were not made. So this is the community. That is one thing. Okay. The second thing is, once you bend this or make a change or make a deformation, then you fix it and then collect the data on the single crystal diffractometer, because these are all single crystals. So then you can solve the structure, and then you can see the difference. Like then you can propose a mechanism, like what exactly is leading to the.
So when you say mechanisms are proposed, these are based on, are they sort of, are they based on some fundamental principles, or is it just phenomenological, or what kind of things are? Because I am amazed to see, of course, extremely exciting, but every paper seems to be something that has attracted or that has merited very, very high level of acceptance.
Right.
So I'm just trying to see where are the challenges in the field.
So yeah, so see, the mechanism here and the mechanism is here is different. Then in crystal engineering community, always it is a question of whether you can design them or not. Suppose here it is a fluorescent one. Okay. Suppose if you have a fluorescence and the color fluorescence, the emission color is changing. So then that becomes interesting. And then you can basically, if you can design it with, for example, conductivity, or if it is a semiconducting material, if you can design that, so design principles are always very important. And if you can study some systems fundamentals very well in some systems, and then understand how it works, if you can design, so that can allow us to design materials with multiple properties. So I think that is where
we go from, I mean, they are not accidental. They are from first principles, you say that this crystal will have this kind of a behavior when it is bent, and then you actually verify that or something like that?
No. So initially, these are only few in the high impact papers, and that is what I'm showing. So now you see papers everywhere, and those are all not in highly restricted papers.
No, they should be. They are really great work. They
Right.
should be there.
So basically, like now people know if you have a very like a corrugated structure with certain angle, and then if you have a good pi stacking interactions or something in those kind of weak interactions, and then you can expect these twinning or domain changes or phase transformations, and this through super elasticity or so you can now predict. So that was the challenge. So that is what we know now. So now people can basically predict to some extent, and then they can go and then do it, and then you will mostly find it true. So that's the challenge. So here again, the same Japanese group have shown that a crystal can be actually deformed to a large extent. As you can see here. So you put a crystal in between these two plates, and then you slide one, and then crystal basically like wax almost. But they could even get the crystal structure at an intermediate stage. So they see that it has a layered structures, and the interactions between the layers are very weak, so you can basically slide them. So that's what they have shown. And here it is a photochemical reaction, and if you put these crystals under light, so they start twisting. Again, here the once reaction starts, so it is anisotropic. So that is why the extent of reaction at different locations is different. So that is why these crystals start rolling, and then you again remove the light, and then you put a different light, then again it comes back. So that is what basically happens here. And here you have a polymerization reaction. In the single crystal, you shine light from this side, and then crystal starts blending, because there is a polymerization reaction that makes the unit cells shorter on one side, because there is a covalent bond. So on that side, the unit cell becomes shorter. On the other side, unit cells are still same, because light initially is absorbed on the front side more. So then there is a deflection. Then if you heat it again, it goes back. So this was reported by us. And so these are the different kinds of things that people have shown. And then you also have crystals which you can pull, like like a copper wire, for example, at high temperature. And this was also totally unknown in molecular crystals. Then you can basically compress, and you can also make them into thin films, and you can put crystals together and then compress, then they stick to each other, kind of a mechanical welding. But here the most important thing is in all these cases, even after extreme deformation, if you take a nice piece of crystal which is transparent and clean, and if you put it under diffractometer, you can get the single crystal data. So that means it retains the crystallinity very well even after deformation. So this we again try to understand it. So here what happens is the molecules here have rotational freedom. Okay. So interactions between the column, these are like columnar molecule packing. So suppose if you have crystal here, if you look at the crystal packing along this direction, so molecular columns run parallel to the needle direction, and then molecules basically rotate along an axis. So that gives them the freedom, more degrees of freedom, and then interactions between these columns are very weak. So then you can basically slide these molecules in any direction. So that gives you all these special properties. So these are called plastic crystals or rotator phases. So this is not a new phase, but in molecular crystals, especially mechanical properties, nobody has shown, in terms of the visuals basically. And also nobody has looked at these from the crystal structure point of view and try to explain. So we could show some of these very interesting properties, and also people did not know that they remain highly crystalline even after you make them into thin films and all. For example, if you need ferroelectric materials, for example, organic material, and mostly you need them in thin film form. You can compress them and then get highly crystalline thin films. So that would be very, very interesting. Some Japanese groups also have done that and shown that. And so these are called rotator phases. And this is, as I said, all these materials have been known for a long, long time. And so you can look at this book, which covers many organic materials, which show these properties. So where are we going to use all this knowledge? for example, in pharmaceutical industry, most of these solids are crystalline. And so here there are a lot of mechanical action, mechanical processes in a pharmaceutical industry. So people will have to take these materials through a lot of mechanical processes. So here, if you understand the mechanical properties, you will be able to solve some of these problems. And then people have been trying to use some of these materials, particularly liquid crystal gels, and some groups, especially in Stuttgart, Max Planck Institute, Metin City, has been doing nice work, and they have been trying to use these for soft robotics. And from University of Hyderabad, Chandrasekhar has been trying to make photonic circuits with this. And so he has a nice review here in small. You can look at this. So he has basically shown how you can use these microcrystals and then make some devices, like, you can make them into different circuits, and then all these flexible crystals could be useful here. So Chandrasekhar has really taken these, optical crystals into a different level. And so different groups are working on soft robotics. I think this will be also one area where one could expect some use of these crystals, but it's a long way to go. So we just started working on the fundamentals. So regarding the rotator phases, we have published this review, so you can look at actually different applications of these materials. And even perovskites have been shown to show these rotator phases. For example, here these the guest molecules start rotating at certain temperature, so that gives you the very good solid to solid energy change, and that could be useful for the barocaloric applications, for example, in coolers like our refrigerators. So some groups are working on this now very actively. So going into the self-healing materials, and as we know, self-healing is not very common, and it's very, very rare. And most of the self-healing, what people have known for a long time, are mostly in the biomaterials. For example, if you look at the bone, once you fracture the bone, bone heals on its own, although it is a very hard and stiff material. It's not like a gel or something. So it heals on its own. And especially the cracks, when they heal, so you have the electrical charges here. So these electrical gradient, these electrical charges basically drags certain cells, and then those cells come here and then start depositing calcium related minerals here, and then they close the gaps. And also bone is known to show flexoelectricity. For example, if you bend the bone, and you develop positive and negative charges on opposite surfaces. So this is also known. People have been studying this and studied this, and then all these are known to, these properties, basically piezoelectric properties, are known to help in the self-healing. But people still don't understand the details, particularly at the molecular level, and these are all very intriguing properties. So, and in the plants also, people have seen the self-healing. And for example, this fig tree releases the latex, and then it heals on its own within about an hour or less than that. So, and then insects also, there are some parts of the insects which also heal. Here again, the covalent connections, dynamic covalent connections have been shown to be playing show a very important role. And even plants and in many other plants. So so there are a lot of mechanisms. So different mechanisms exist, and people have been looking at all these mechanisms in nature. And so particularly in soft gels and polymers, already some nice progress is made. For example, if you look at this, so it is a cross-linked polymer. Here, when you put these two gels together, hydrogels, and then they basically quickly attach to each other and they heal. So because once you put them together, so they start interacting, and then these bonds are basically, this works on the hydrophobic interactions. So they start.
Malla, can I ask a question?
Yes, Ankara.
So when you're looking at these self-healing materials, what would be the design principles for a chemist to select from? Because I'm guessing that would be very critical in, otherwise you will just go for a, a search where you will be making materials and trying to see which self-heal.
Exactly. So if you look at here, particularly in these cases, natural cases, here you have a, so you have a cross, basically alcohol here, and then you have an iron here, metal, and then this forms dynamic bonds. It can break easily and then it can form easily. Okay, so these kind of iron oxygen bonds have been shown to be important in some of these biological materials. And then some groups have taken similar kind of moieties and then incorporated into polymers, and then they could actually achieve the self-healing in those kind of polymers. So this is there are some design principles, and then even
so the coordination bonds are breaking because from mechanical stretching, and then again they are healing. Is that what is happening?
Exactly.
Is there some, like, you know, the studies going on in trying to understand like what is the strength of the bond? Like if you could predict, let's say, you know, if I had a list of things, I had the strength of the bond, and then how does it correlate to mechanical strength, then I would be able to decide, for example, and fine tune the properties.
Yes, yes. So there are different approaches actually, and the bonds which are very easy to break, those have been attempted, and people already know some. So I have not put on the slides, but there are different bonds which are easy to break. And so, for example, sulfur bonds, right? So they can easily break. And there are several examples where you have very weak bonds which can be easily broken and formed. So again, this is I think maybe it is 15 years old field, so people are still trying to understand. Molecular level details are still not very clear, but this is again a hot area where people are trying to understand. So here again, if you see in this case also, you have hydrogen bonds. Okay, so there are polymers which are cross-linked, and then you have these groups where you have these urea type of bonds. So and they sometimes also put very bulky group next to these on the nitrogen, for example. If you put a very bulky group, so then there is a lot of steric hindrance, and then that makes the carbon nitrogen bond weak, and then that allows you to easily form them and easily break them and reform them. So because to break, the energy is very less here. So these are the tricks people play. So you are breaking the covalent bond still, that's not so easy, but you have to get the design right. But these are the things that people have already shown that they know that you can get them. So again, here the diffusion is important here. They have to be soft, and then you also need to have a lot of hydrophobic regions as well. That allows you some kind of a local mobility for the molecules. And then you need some hydrogen bonding groups or weak covalent groups, which allows you to break and form. Because once you break a covalent bond, then there is always a driving force for recombination. So that drives the self-healing. So that is what people actually found in some of these materials. And then there are also different approaches. Suppose if you have a polymer, and then you take a monomer, something like this, and then you have a catalyst, and then you make kind of a composite where you have regions where you have liquid monomer, and then you have regions where you have catalyst. So you basically somehow you manufacture it when you make it, and then you have all these regions. And then once there is a crack, for example, and then crack randomly will run through the material. But whenever it hits a bubble with a solvent, and then that would come out, and then there would be also some regions where you have a catalyst, and then it will start react. The materials will start reacting, and then the liquid would flow through the crack, and then you have a catalyst somewhere, and then basically there is a polymerization reaction. So that will fill the gap. So then again, you kind of a self-heal. So this is an indirect engineering. Mainly, it is not a you're not making a molecule to self-heal on its own, but this is a kind of a engineering design. So these are the different approaches people take. So here we can achieve this in even hard polymeric materials actually. So, but again, it's not very easy to make these kind of things, and it's not doable in all types of materials. But as a proof of concept, people have already shown such things. Again, here, if you look at this particular example, it is a polymer again, urea-based polymer. If you look at here, they put a bulky group, and then this bond becomes little weaker. So, and once this becomes weaker, then you basically form a ketene, and then you get a amine, and you break this covalent bond, CN bond, and then this again they can react because these are not very stable. And then that is how when you make a crack in the polymer, and then when you leave it again, put it back again, they react, and then there is a self-healing. So these are the different methods. Yes.
Malla, I have one query. So So your observation are more like at a bulk scale, and you are connecting that to a molecular scale bond breaking. So how do you monitor these, that there are these type of bond breaking?
So see, these are from different groups. Okay, so this is from the literature. So they have done characterization using spectroscopy techniques, different spectroscopy technique. For example, if you see here, I think this is probably from the IR. This is from the IR. So you look at these bonds, like, these reactions are very well known. So you look at the changes in these bonds, and then you know that there is a reaction. So people have characterized using different techniques. Yeah. So here again, if you see, this is a very soft material, and most of these materials are very soft, and either they are like gel or or like elastomers. You can stretch them. So achieving self-healing in very hard materials has been very, very difficult so far, and not many people have achieved. Even after self-healing, your healing percentages are not very large most of the time, or you need to heat them or put them together for 24 hours or sometimes 40 hours. Then you have some healing. So it takes time, and most of the time it happens in only the softer materials. You need diffusion inside the material, or sometimes you need to also heat, or put them under light, or you have to give some stimuli. So that is the difficulty, and always people try to achieve it without any external direction. For example, if you see here, and this is also very soft polymer, and if you cut it after, I think, certain time, then again it heals, and so it is again based on the hydrophobic interactions. So it is again a very soft material. So these are the things that people have shown in the literature, and people also have made composites of nanomaterials coated with the polymers, certain type of self-healing polymers, and they have also shown that self-healing can be achieved in the composites as well. And here again, self-healing polymer has been used, and people have got self-healing in the composite materials as well. So all these are from the literature. And then when it comes to crystalline materials, so it is a big challenge, and not much is done. There are only, as far as I know, there are only 3-4 reports. And even in all of these, self-healing happens only under very, very special conditions, which are not very, you cannot expand some of these to other materials. For example, if you see here, it is a protein and a polymer composite, kind of a hybrid material. And if you take these crystals and then put it in a salt gradient, salt water, or I think it's a buffer, then there is a swelling. So when you have a swelling, then there are cracks, and then after some time these cracks vanish. Again, you change the salt gradient, concentration of the salt, then again it shrinks, and then there are cracks, and then these cracks again heal in the solution. So this is all done in the solution, and crystals in solution, you can always play around, and then most of the time, because there is a dissolution and then recrystallization, so this always tries to eliminate the defects. Even if you cut a crystal into 2 halves and then put them into the liquids, so into the solution of the compound, then again the crystals can actually grow the other part. So these are all known, but in solution it is understandable. And but if the material is very hard, in most organic crystals it was not possible, and because you have a high organic crystals are mostly very stiff. Any crystalline material, they are typically stiff and rigid, and diffusion is very difficult in solid like crystalline materials, and fractured crystals break into many pieces or develop uneven fracture surfaces. That makes the healing very difficult, because these are mostly hard materials. When you try to put them together, you don't have enough contact if the surfaces are not very smooth. So that leaves you to basically it doesn't allow you to basically put the things together very nicely. Then
Malla,
yes.
Malla, sorry, I didn't want to break. We are not going to take any more questions because the 15 minutes are remaining.
Okay.
So you cover the part, and then with the end we will take fresh questions. Okay.
Sure, that's perfect. So here then in organic crystals, other groups have shown, this is done by Panche Nomo from Abu Dhabi. So they have shown that if you take a crystals of this molecule, and then you break it into 2 pieces, you basically put on 2 plates, and then you make a cut and then pull them apart. You have a crack, then you put them together for 24 hours, and then there is a kind of a healing. You still see a big crack here. So then when you pull them apart, you see that it is 7% healing. So this was the first example, kind of a first example. I think there might be 1 or 2 other types of healing it has been shown, but those were slightly different. The different mechanisms were different, and it was not studied in a proper way. And so here another molecule they have taken with these these boron oxygen bonds, and again this is a very soft material. It's a very really soft material, and then you again break it into two pieces by attaching two plates on either side, and then you pull it, you have a crack, and they separate. Then you push them together and then keep it again for hours, and then you push them back. Then you see about 75%, 67% healing in this material. So these are only the two significant ones in the organic small molecule material. So these are very soft material. This one is really soft, and then you have to put it for hours. I think it is 24 hours if I'm not wrong. And then you still see a big crack here, and then this remains as crystalline, but its crystallinity is not maintained here, so it really gets damaged. So, but it is again a very important contribution, and this also inspired us in some way. And then we were looking for some examples. So then we got into this particular case. So this is a bipyrazole derivative, and you have methyl groups here. This kind of a steric interactions you have, and then you have nitrogen and then NH group here. So so here we were working on this system for some other purpose. Basically, you have both hydrophobic groups as well as hydrophilic groups. This was our idea to create, design some particular type of mechanical property in somewhat networked crystals. So we thought of having a kind of a three-dimensional network where you have both weak interactions as well as strong interactions. We wanted to see how the crystals would respond in terms of mechanical properties. So my students was looking at these crystals. So he found most of these as brittle crystals. Okay, these are hard and 0.4 to 0.5 GPa hardness, and then elastic modulus is 8 to 15 GPa. This is quite high for self-healing materials. And then these are single crystals, perfect single crystals, and that you can't expect diffusion in these particular crystals because they have a three-dimensionally hydrogen bonded network. So mostly you don't see any diffusion. So when we were looking at the mechanical properties, my student found that when you push very gently and you have a big crack, and then these crystals basically it pulls on its own, and then they rejoin, and then you have a crack, and then it goes off on its own. Okay, so and once it heals, the healing is actually it's perfect. Actually, you don't see any sign of crack there. Okay, so but when you push it hard, and then you can see here there is still a crack. Basically, it doesn't heal completely if you push hard, but when you gently push.
Well, I have one quick question.
Yes.
So what I see that wherever you push, the crack is at only one specific spot.
Exactly.
So is it
So
like a defects or something plays a role in where the cracks are?
Here, basically, once you crack it, so here this is the weak point, and so it is not 100% healing. So once it cracks there, that means basically this is the weak point. So wherever you push it, so it heals there. It basically cracks and heals there again, because that is a weak point. And once you make a crack, you don't expect 100% healing, even in the other materials as well. Of course, there are some other materials, there are different mechanisms where crack region becomes much harder. But here in this case, it is not 100% healing as it suggests. So wherever you push it, it basically cracks exactly at the same place, because that is a weak point. But most important thing is it comes on its own. You don't have to push it to put together. And when it heals, it actually heals perfectly. Even after when there is a visible crack, and still they hold together, and then they nicely sit together. And this is another slow motion video. As you can see, it is a big crack. When you release, then it is completely gone again. So this is, and again, when you release the stress, so the crystal pulls back on its own, right? So the two pieces come back on their own, as you can see, and then they heal perfectly.
Excuse me?
Yes.
What is the time scale of this movie?
This is less than a second, maybe a couple of microseconds to maybe 10 microseconds, this healing part.
Okay.
Once you release the stress. So it goes back in maybe microseconds, basically. Yeah. So this is another one. Again, this is a slow motion video. It was taken at 500 frames per second. And when you release, once you crack and release, so there is a lot of attraction, and then that leads to kind of a motion. We were very surprised to see this kind of motion. Normally when you release some cracked piece, so it just remains there. So here this suggests that there is some kind of attraction here between the two particles, and that is why they are coming closer. So then we wanted to understand that. Again, you can see here, you just push a cracked crystal, and so again this whole thing jumps, and then there is a lot of motion here. So that is because it appears that it appeared to us that there is an attraction. Then we got curious, and then we wanted to see if you push these particles, once you break them, bring them closer, whether they basically attract. So as you can see here, this is again a slow motion video. So this piece basically jumps onto it. Okay, so this was about 50 microns distance. So the attraction is at a long range. So this 50 microns is quite a lot actually for a kind of attraction that you see here between crystals. So, and again, as you can see here, so healing is perfect here, and you don't see anything in the optical microscope. We have also looked at under SEM, and we have looked at under confocal microscope by doping with some fluorescent materials. So we did not find any crack in cases where you see perfect healing. But there are many cases where you don't have perfect healing. That perfect healing doesn't happen. For example, if the crack is not linear, or if some debris fall in between, so you don't have a good crack. So
what is the template on which you have kept the crystals? Is this on open air, some template, some surface?
Yeah, this is on a glass plate. Okay, we look at it on our microscope. So these are basically forceps.
And it's on a glass plate, nothing else, no liquid, nothing, right?
No liquid. So from this side, you are pushing with a needle, metal needle, and then you see a clean healing here, right? So if you look at in a real time, for example, so this is the real time scale. Like, as you can see here, yeah, that's how it happens. If you just press, then you have a crack, and then it generates. So this is a slow motion again. If you push on top of the crystal, you have a crack, then you release it, and this crack completely goes off, and then you don't see any sign of crack there. So it is a very clean healing. So this is what makes these materials very, very interesting, because most of the time, and also it is very, very fast. So it is very fast, and then it heals almost like atomic level perfection from these images. But then we wanted to understand how well it is healing. So then we did different measurement. As you can see here, so this crack did not heal. Most of the time, if you press very hard without gentle push, so if you just push them, they all break like other crystals. So, but then when you bring two pieces closer, they again get attached, and then they are together. You can move them, so they nicely attach to each other, even if you separate them and then bring back again. So then we did a lot of characterization. Then we looked at under SEM. So we didn't see any sign of crack in cases where you see the perfect healing. If the healing is not good, most of the time we found a non-linear crack or some debris inside. So healing is not perfect in such cases. Wherever you have a good healing, so we mostly saw a very nice linear crack without any debris in between. So in those cases, the healing is very, very efficient. So what is the origin of self-healing? So we wanted to understand. Then we looked at the crystal structure. If you look at this crystal structure, you have a water chain, polar water chain, and all these bonds are actually aligned in looking at it in one direction when you look at the polarity of the bonds. So it is basically a polar hydrogen bonding chain, and then you have these bipyrazole molecules which are connected to this network from both sides, and then these water molecules are kind of sitting in a channel. So then these water molecules, all of them are going in one direction. So they are all polar, and polar direction is in one along the needle direction, and they are all aligned in one particular direction. So all the dipoles are aligned in one direction. So it is a tetragonal crystal, a polar space group. So this is actually a piezoelectric space group. And then you have also hydrophobic groups, because you have four methyl groups on the molecule. So all these hydrophobic groups come together, and then they form hydrophobic zones. And then you have hydrophilic zones where you have strong hydrogen bonding interactions. So it is a kind of, you have a three-dimensional hydrogen bonding network, because these bipyrazole molecules are also attached to this water chain, and then they are all connected through hydrogen bonds. But in between, you have hydrophobic regions with these formed by these methyl groups. So this makes it special. So these are the water chains that you can see different hydrogen bonding interactions. And we did nano indentation to see how hard or stiff are these materials. And they are compared to many other materials. So these are very stiff. And healing is also very, very fast. In most of the cases, healing takes hours, 2 minutes at least. And or you most of the time require either heating or you need a catalyst or something else like moisture or some other stimuli. So it is very, very rare to have a hard material or stiff material which heals very fast, and there is no external direction, and also there is no diffusion here. So the mechanism is totally a different, it is a different mechanism. So that is what makes this mechanism very unique compared to most other materials. So then we wanted to understand what is causing these pieces to come together. So what is the origin of the attraction? So as I said, this is a piezoelectric space group. So when you apply the mechanical stress on piezoelectric materials, so there will be basically anisotropic distribution of the charges. So you disturb the charges. So then you generate potential. And then when you release, if this material is a true elastic material, and it would recover completely, and then you don't see the charges. So then it goes back to its original position. But suppose if it is a slightly a plastic deformation, if it's not 100% elastic, then you would have some partial charges, right? Some charges would be still there on the surfaces. So since it is a piezoelectric material, and then we wanted to study with the PFM instrument. So basically what you do here is you apply voltage bias here, electrical bias here, and then since it is a piezoelectric material, when you apply bias, electrical bias, so there will be a mechanical change. So then material either would go down or it would basically bulge out. So locally, that would give you the estimation of the piezoelectric response of the material. So we have done this. So then we understood that this is a good piezoelectric material. For organic materials, this is not really great, but this is also not very bad. This is moderately good piezoelectric material. Then we have also done the piezometry measurements with the bulk crystals, and then we again found that it is a nice piezoelectric material. And then we have done different measurements on the broken crystals. When we did the experiments on broken crystals, we see slightly a lower piezoelectric response. That means there is some fatigue in the crystals. So that is why the crystals are not as piezoelectric. The response is not as good as in the pristine crystals. So this tells that when you deform these crystals, there is slight possibility of a plastic deformation. So that is why there are some defects, and there is some fatigue in these crystals. So even in the pellets, we saw that there is a slight drop in the piezoelectric response, and this is not surprising. So this is true for most of the piezoelectric materials. When you deform them, when you have a lot of defects, so piezoelectric response is expected to be slightly lower.
Sorry, Malla, sorry to interrupt, but the axis you sort of have written on your diagram is a 0, 1, 0. So is that along the shape of the needle? Because I was going to come back to this, but I just noticed it in your diagram as to.
Okay. So needle direction is the 0, 0, 1. Okay. So this is the 0, 0, 1. That is the needle direction. So this is the face basically, which is perpendicular to the 0, 0, 1 face. Okay, so this is C axis. You can say this is the C axis, along the C axis. So if you write it with a square bracket, that would be 0, 0, 1. That is the direction.
No, I understand. So in terms of the deformation or the mechanical stress is being applied along which axis then?
That is applied along the 0, 1, 0 axis. So that is the B direction. So this is, you're right. So we are not applying the stress along the polar direction of the crystal. So you're applying somewhat at the 90-degree angle to that.
Okay.
We have not done the measurements on the tip, so that might give us slightly different piezoelectric response. So
okay.
100 and 010 are crystallographically exactly identical because it is a tetragonal crystal. Yeah. So then we broke a crystal, and then we wanted to map the potential, the electrical charges here. So we used Kelvin probe force microscopy. Here, what you do is your tip has a electrical bias. I'm not an expert in this. Excuse me if I say something wrong. So what you are trying to do is to map the electrical potential here on the surface. So you basically go around. It is exactly like AFM. So it will just map it here, and then you basically know how much potential, electrical potential you have on the surface. So we see that it is an average potential is around plus 4.72 volts on this, which is quite a lot. Because this is after 15 minutes of the breakage, because we have to make the sample, and this took about 15 minutes. And the first run, this was the maximum that we got, but in other crystals we got less. So it is about plus 4.7 volts. So that means the surface is positively charged. So then we looked at more crystals, and then on some crystals we found negative charge, negative surface potential, and on some crystals we found positive surface potential. So on these crystals we could not really determine the polar axis direction. So since we have not done the phase indexing before doing all these experiments, we really don't know what is exactly the orientation along which you get positive charge and along which you get negative charge. But what is more important is that you have on some crystals positive charge and some crystals negative charge. So, and we also looked at a crystal with a crack. This was not a very good self-healing crystal. Self-healing was not very efficient. We had a crack, visible crack, but still the pieces were together. When we mapped it here across the cross this crack line, and then we found on one side negative charge and on the side positive charge. This also tells that there are opposite charges, and when it is not fully healed, there is a remnant charge. So that means when there is no healing is not efficient, so then you have a penalty here. So it has not reached its optimum stability, right? So you still have charges here. When we did the experiments on the perfectly healed crystals, we did not see the gradient. We saw some potential, but it was not a gradient, not from positive to negative. So that tells that these crystals, when they heal perfectly, so you don't have remnant charge, this charge gradient you don't have. That means there is an advantage if it heals properly. If it doesn't heal properly, so then it doesn't optimize the charges properly. So that means there is a penalty. So this basically drives the crystals to achieve very good self-healing, and probably that is the reason we don't see any sign of crack when these crystals properly heal. Okay, so then as I said, to summarize, this is the mechanism. You have these hydrogen bonding interactions. You don't need to have water. We have other examples where you don't have water. Jedi, I'm finishing in 2 minutes. So then you have polar direction. When you crack it, then you have on one surface you have positive charge, on the other surface you have negative charge, because it is a kind of a head to tail arrangement. And so this leads to the attraction of the pieces, and then when they heal properly, so then you don't have remnant charges. So that is what probably is making them align properly. And then we also looked at single crystal data from the nicely healed crystal, and we found no sign of fatigue in these crystals. X-ray is not a very good technique to know local changes, but an average it tells that it is still a very good crystal. So you can get a perfect diffraction data from it, and you can solve it. You don't find any difference between pristine crystals and neatly healed crystals. So you see the diffraction patterns. Even at higher angles, we found beautifully sharp peaks. That tells that at the level of X-ray, at least you don't see any sign of damage in these crystals. So, but if the healing is not clear, not good, so the domains are not nicely aligned. So that is why you see split peaks. So this domain and this domain, they are not fully aligned. So there is a mismatch. So that's what we could see from that. Then with my colleague Nirmalya Ghosh, so we have used the Muller matrix technique, and this is an optical technique, birefringence technique. So it allows you to basically see the polarization, different components of the polarization direction. So my colleague basically he built this technique here. He's an expert on this. There are not many people who do this, use this technique at this level. So then we found a perfect technique to actually probe at nanoscale. So the resolution here is about 300 nanometers. And then we looked at pristine crystals, neatly healed crystals, and imperfectly healed crystals. And we found that neatly healed crystals are about 10 to 15 to 20% lower in terms of the order compared to the pristine crystals. So these are the best. And then neatly healed crystals have at least 10 to 20% lower order. But imperfectly healed crystal, whenever you see a crack, so especially the area where you have a crack, it is about 50% drop. So this allowed us to quantify, but in X-ray we could not find any difference between these two. So this tells that this is a very good technique, and we can go to at least micrometer, if not nanometer, and then we could see these changes in the parameters. I'm not going into the details here, but this technique could give us quantitative estimation of the self-healing. So so this tells that self-healing in our case, whenever there is a good self-healing, it is really good for the crystallography purpose. So you don't see much difference in the neatly self-healed crystals. So these are the parameters. Again, I have already explained this. So if it is neatly healed, the crystallinity at the nanoscale, don't forget this is a nanoscale crystallinity, but for single crystal XRD, you don't see any difference. That would give you 100% efficiency, but at the nanometer scale, you have 80 to 85% if it is neatly healed. If it is fragmented, you just separate the two pieces and then do it. It is 85 to 90. And if it is badly healed or imperfectly healed, that there is a big drop. So there is a penalty. That is why, to avoid this penalty, most of the time when there is a chance, it would go to a neatly healed. So that is the driving force. So we had more other examples, and we have also shown that it happens in piezoelectric crystals, and but it doesn't happen in all piezoelectric crystals. We found that this is a very stiff crystal. We don't have much plastic deformation in this crystal. That's why there is no attraction. We could not see much attraction, but we have to study these more. And with this, I conclude basically. So soft crystals are attractive for various applications. I think in the future, probably we will find some more applications. And self-healing in crystals can be found if they are polar type. And probably polar crystals can be explored further to understand the design principles. Self-healing crystals may provide insights into ordered natural materials, for example, biomaterials and all, how they heal, for example. It is difficult at this moment to quantitatively study self-healing, but with Muller matrix techniques, probably we will be able to, or maybe there might be many other efficient techniques. So we will have to find out. Then I'm just trying to ask a question myself, and then I'm addressing the audience now to help if some discussion can be done on this. For example, if you look at microtubules, all these biological materials are more or less polar, right? So these are all mostly built up with chiral molecules. So suppose if you have polar direction, and then if you bend them, so when they are under stress, these microtubules, when there are defects, so they on the inner side, some material, these molecules go out, and then stiffness decreases. When they become straight, again they repair themselves. So these are all polar molecules, polar basically structures. So I'm just wondering whether there will be a similar mechanism, or there will be any overlap, or there are any contributions from the piezoelectric effects that we can see in these materials. For example, if you break these into two pieces, would you see opposite charges? So if these are observed, or if you see any kind of overlap with our mechanism and these biomaterials, I think that would allow us to go into more details. But at this moment, this is just an hypothetical question. But since they're also polar, there could be some need into that. So with this, I conclude, and thank you very much for your patience and nice discussion already. Thank you very much.
Very nice, Malla. Thank you very much. I would like the audience to please give a warm round of applause, muting their audio. This was a fantastic talk, very exciting at many levels, and of course raising a lot of questions, further questions, which I think some of them will be done by the audience here right now. So I see two show of hands. Ankona, you could go first, and then Shudhita.
Yes, fascinating, Malla, and congratulations. So one thing that I'm wondering, so it seems like the charge, this difference that you're seeing on both the edges is helping it come together at a molecular level. Again, chemistry question. What do you think is leading to this charge differences at the crack?
Yes. See, it is not yet clear, but this is my guess. See, we see some fatigue. That means it's not a very perfect alignment. So the molecules have, it's a polar arrangement, first of all. And once you move the molecules away from their thermodynamic positions, okay, so then the charges are imbalanced. So that is probably causing these charge separation. So this is typically we see in piezoelectric materials. So when you compress, so on one side you have positive charge and the other side you have negative charge. So this potential gradient, basically you see a charge separation, right? So a similar kind of thing might be also happening here, because you see a permanent deformation to some extent, like 10 to 20% at the local order. We see at local level, we see some deformation. So
your molecule is a polar molecule, I mean, or the arrangement is polar, you think?
The arrangement is polar. The arrangement, supramolecular arrangement is polar. The molecule itself is kind of, it has polar groups and then some, less polar regions, but the entire arrangement is polar.
Yeah, so you think some structural changes might be occurring that is leading to the charge separation, or?
You mean at the supramolecular level?
Yes.
Yes.
Because this is a big charge separation that is happening, right?
Yes. Yeah. So I don't know how much is 4 volts actually, right? How much of deformation is required to achieve 4 volts on a surface at a micrometer scale. So I don't have any idea about that, but I think I think we need more study definitely, and some calculations might help. But again, I talked to some people, they said these are very challenging if you especially want to get some quantitative estimation. Like, molecular dynamics, for example, if you distort and then see whether you can get something. I'm not sure if something can be done in those lines.
Thank you.
Yeah, thank you very much.
Okay, Shudipto?
Yeah, hi Malla. It was very nice talk and very nicely given. I learned a lot. I am coming back to this question of your local loss of order locally, but globally having the order, because if I look at the X-ray crystallography data, your two pieces, suppose two pieces have come together, they must be perfectly in alignment over a length scale of the two pieces. Otherwise, you would have this duplication that you showed in one of the things, duplication of peaks.
Peaks, yes.
But I guess in some you don't see the duplication, right? Or
yes.
You see it in all?
No, we don't see in some.
Okay, so that means if across a macroscopic length scale, they're perfectly aligned.
Right.
Otherwise, it's. However, if you go with the Muller matrix, local polarization microscopy, you see there is some loss.
Yes.
So
in case of the perfectly healed crystals, where we don't see any sign of a crack, okay, visually or optically, like, or in the X-ray, in those cases, we don't see a dip at the crack junction. Overall, we see slight dip closer to that, very like 10 to 15%, but we don't see any sharp dip at the
no, but you still see a 10 to 15% thing. So that's what is intriguing. I find intriguing, because I thought if over a long range it is perfect, then locally also it has to be perfect. That means at the interface, some of the bonds are not being made. Okay, somehow, even though mostly they're exactly aligned. So is this some chemistry? They got oxidized or something that actually is not able to make the bonds? Or is it some plastic deformation somehow is not being able to come back to the crystal structure? What did you think?
Yeah, so
is it chemistry?
Yes, I think these are inert molecules. We have a range of molecules. They're all, I don't expect any chemical changes in those. So going by this, since we see the plastic deformation as well. So I think this is at a supramolecular level, you have some kind of a mismatch in the bonds. At this point, I would only guess it is all at a physics level. Not at a chemistry level.
So that means, if I draw a potential energy diagram of the alignment of the two neighboring things, there is some flatness in that diagram, so that they can come close by 10% of the molecules can come close, but still doesn't find the minimum, which must be the right crystal structure.
Exactly. Yeah. That's the right way to.
Interesting. I thought these things would be, they'll like fit like a jigsaw puzzle. That doesn't.
Right.
Okay. Thank you. Thank you for a nice talk.
Yeah,
okay, we have people who have raised their hands. We have Shovik Chatterjee. Could you ask your question, Shovik?
Yeah. Hi. Yeah, it's a great talk. I have actually a question regarding this cracks that you were showing in the later part of the talk, like when you were pressing and there's a crack was happening at a particular place. So I was just wondering if there are ideas about, if you can relate this propagation of crack to the crystal structure, because in the mainly inorganic materials, we know that how this dislocation propagation is dependent on the packing of the atoms. So here, is it related to the crystal structure, or is it completely like random? Or so if you can throw some light into it. And this also goes back to some of the initial slides when we were talking about the mechanism. So I was wondering how well we understand this kind of how we nucleate dislocations and how they propagate vis-a-vis, for example, the 3-5 semiconductors, where we know well, but not very well, but at least some idea we have.
Right. So yes, there is definitely a relation to the crystallography, crystal structure. For example, if you look at this, can you see this now? Yeah. So this is the plane that we are talking about. So this is so now you're looking at along the needle direction of the crystal, okay, long axis of the crystal. And then when you break it, and this is the surface normally you would see, okay. And here, if you look at from the other axis, so this is the 001 is the top one. So this surface is basically 001. So you're looking at along the C axis, and this is the surface that you open up when you break it here. Okay, so that means then now this is a different axis, perpendicular axis. This is a long axis now, and when you break it here, probably you would break it. Okay, so this is the axis where I expect these to break. Going by the phase, when you do the phase indexing, and you see that this is parallel to this. So these are the bonds which are breaking basically. So these are the planes. So this is it's not a very weak plane because you are cutting through strong hydrogen bonding interactions as well. But this is where you don't have covalent bonds. You can, of course, it's not atomically flat. There is some kind of, it's not a flat one, but that is where you have a slip plane. You can say it's a plane where you can break through covalent bonds.
I see. And you always get the needle direction along 001 for this.
For these crystals, under the conditions which we grow, they always grow like that. Yeah, but we have not tried in different solvents. That can change the shape, and that will be again, you can change. Yeah.
Okay.
Yes. Yeah. Thank you.
Okay.
But for other crystals, like I have not shown so much today, but for plastically bendable ones, and then these ones which shear, in all those cases, these weak interaction planes and crystallographic directions and planes are very, very important. So although I have not shown some of them, but you are absolutely right. All these are very important, and we very much look at all those before we analyze this crack direction and the plane.
Okay. Yeah. Thanks.
Okay. Shankar, could you ask Shankar? Shankar, you're muted. Shankar, you're muted.
When you break a crystal, the surface, does it undergo reconstruction? So here is my very naive question. Is this what I'm joining together? Is it the original thing that I'm joining with all the bonds which is like zigzag puzzle mixing, or am I just basically gluing something which is slightly disordered?
I see at an atomic level or molecular level, what exactly is happening is very difficult to say, but I think it is basically like, you would still expect some kind of a mismatch somewhere. It is very difficult for macroscopic, material to align completely at atomic level. But it is more or less like, it's the two particles are coming almost like, close to the perfection, but I don't think that is really a perfect alignment. Because there is slight plastic deformation, so you may not have completely matching surfaces, right?
So this is what I was trying to. Okay, is it? So I'm getting this gluing up. Is this gluing up is basically driven by the charge separation? That's what I understood. Yes. Charge separation, and that's what is like. This is why it's like electrostatics, which is just bringing the two things together, right?
Exactly.
And,
that's right.
And typically the way one thinks about electrostatics is a diffuse layer. So the charges are kind of like, they're screened over, all of kinds of things. And this is why find an electrostatic giving rise to something which is a zigzag fitting is, I don't understand the picture actually.
No, jigsaw means at what length scale?
At the length scale is bond to bond. Suppose I say that, this were my bonds and this were my other set of bonds, and they just like that's what I would think is an ideal gluing up of the object. This is why probably your X-rays and everything would exactly match.
Right, but see, I think what happens here is almost like a perfect matching. But I don't have any proof to, or I don't expect that it is a 100% matching, but there is a very good match at a molecular level. So that is what I can see, because whenever there is a perfect alignment and we don't see any charge gradient actually, both it is
so
either
surfaces don't reconstruct when you break them.
They reconstruct. Yes, they reconstruct. I think when they come close, I think again they reconstruct, and that is how it is able to release a lot of stress. So then it is able to align, because you also, when you see the two particles coming together, and there's a lot of motion as well, right? All this is basically shaking the whole thing again. So even at the molecular level, you expect a lot of reconstruction. But again, this is all is a guess. But since you see a very good perfect alignment, and even in the AFM we didn't see any kind of a step, so this tells that it is a very good alignment. But whether we can say at a molecular level this is happening perfectly, that's, I think, very difficult. Yeah.
Okay. Vivek has a question. Vivek, can I ask a question before you?
Yes, go ahead.
Malla, one of the things that over a period of time the audience have been getting at is, and in fact ended with Shankar's question, is the perfect alignment. So have you ever considered a possibility that you have proton transfer events at the interface, and those proton transfer events are connected through hydrogen bonding at the interface to have a perfect matching? So with hydrogen bonding, it's very well directional, and there is no question that you have diffuse charges. See, anything at the bulk level, you can say, oh, there is a diffuse charge there, oppositely charged. Now, the question would be to test it out. You break two crystals. You don't know where those crystals or broken pieces of crystals are. Bring them together. Ask the question whether those two independently broken crystals can be reconstructed again. So if it was just charged, I would say yes. If you just collect the right charge components, right, I would say it will perfectly fit. But I believe it's not, because if you do this experiment where you break two needles separately and there will be 4 combinations, you will look at 2 combinations that will work out. So if that is the case and it's just the charge, then that would create those 2 perfect crystals afterwards. However, my point would be, it is much more deeper than just that, simply because you have perfect alignment. And so the perfect alignment can only appear with molecular forces at the level of directional bonding. So if there is a directional bonding, and this can be tested, just make the NHND, okay, and look at the rate at which the crystal fuses. So you will get a kinetic effect on the rates. So if you were to just do an isotope labeling of the sample and look at that, is that possible? Is that what, have you ever considered that? Yes, this will still not change it chemically much.
Right.
Just that it will be a charge effect, local charging effect on the atoms, not just on the supramolecular structure.
Yeah, it's a very nice question, Reddy. So I agree with you that there is a possibility of protons coming into picture, dynamic effects and all, very much possible. But so coming to this, changing proton to deuterium, it's very difficult to quantify how much they are coming. But if there is a significant difference, the speed they come at, or we can actually quantify the forces that you have on the surfaces, based on the
yeah. So what you would require, would you require? You would require a binding isotherm measurement, something similar to what surface people do to separate physisorption versus chemisorption. The way classically it is done is you were to look at what is the coverage of the monolayer, right? And you would look at the sort of the isotherm. So the isotherm will tell you whether this is chemisorption based on the amount of energy that is gained after the binding event versus physisorption. So if a similar experiment could be planned where you don't, you break, maybe you remove a monolayer of molecules or a bilayer of molecules from the crystal and then again reform it. It would almost serve like a isotherm, you can measure the binding isotherm of such an event. That could be one possibility of looking at the interaction energies. The other one is what I'm just saying is a macroscopic experiment. Break two crystals and see if you can bring them together. If there was no signature of which atoms should be connected to which atom, it's only purely electrostatic. I can bring two of them and join them as a perfect crystal. Why am I not? So if I do this experiment, I don't know what the result is. But if I'm not able to do that, it means that there was a memory of how it was broken, and some charges have an atomic signature. You will have certain broken bonds which will have to reform. Only then it will be perfectly healed. So
yeah, I totally agree with you. When you break these crystals and the way it is broken, that the extent of charge you generate on the surfaces, it influences basically the extent of. So we have also seen that the way you break, there is a difference in the amount of charge that you see. Right. So yeah, you are absolutely right. But I think to quantify these, I think we need very carefully designed experiments. So
yes, of course, of course.
Yeah,
but
this is very interesting,
fascinating.
And we can do it really. That would be really nice.
Yeah.
So, yeah, we can probably discuss more about.
Yes, we will discuss.
Yeah,
sure.
Yeah, this is
Vivek. Sorry, Vivek, I took your time, Vivek.
Yes, Reddy. Yeah, amazing talk, Malla. I have a very quick question. So, is the repair environment dependent? What I mean to say is, while repair, if you have some ions in your solution or some charged nanoparticles in the solution, is it possible to then have them doped into your crystal?
Yeah, so this is very interesting, Vivek. So we thought about this, and my students have recently checked the polarity of the solvent, and we see very weak response of the is attraction response in polar solvents, very high polar solvents, but in silicon oil or hydrophobic oils we see a very good response. So there is some dependence of the medium, but again quantification is little difficult, but we see a clear difference when you go from one end to the other end. If you take highly polar one and non-polar solvents, we see some difference. Again, doping is another interesting question. So I think if you can dope and create it, imbalance more, and then the way it breaks and the amount of plasticity you can get in your doped system. So all these I think will be very interesting. Definitely, I think there will be some influence, because people have shown that even in a centrosymmetric crystal, if you dope with certain non-centrosymmetric materials, so you would still see some kind of a polarization response. So you can always disbalance and break the symmetry, and then you can make the materials become little polar. So I think definitely some of these will be an interesting things to do.
Yeah, thank you, Malla.
Jyotishman, can I go with the question?
Yes. Oh, I'm sorry, Sushil. Yes, please.
So that was a very nice presentation. Okay, very impressive. I wanted to ask about this particular phrase, your healing duration, which you mentioned. Is there some sort of an analytic relation between the healing duration and the crack depth? I'm using the word crack depth because I don't know how to quantify it. And the other question is, the depth is a linear dimension. Would it actually be related to area? How would you look at it?
Okay. See, we have not thought about this enough actually, but we thought about it, but not enough. We see some correlation. If you have, for example, if you have a crystal which is plate-like, depending on which from which side you break it, so we see some difference. But again, this is little complex. So suppose if you have a flat crystal, like a plate-like crystal, and if you do it on if you land the crystal on the flat surface, and then if you push it from the side, so the crystal nicely, it's on a flat surface, right? So you also have in the same direction enough surface. So that's slightly different. But if you put the plate-like crystal perpendicular to the surface, then if you make it stand, then if you push it, then you don't have enough surface in the pushing direction. So in that case, we did not find a very good response. So, but I don't know, but then this is a little different, right? So you don't have enough surface on the other side to pull it back. So this is a little bit tricky. So I did not basically get what exactly is going on, but definitely we see some difference, but I don't know how to interpret that. Which effect is basically acting is not clear to me. So
Okay.
I hope you got what I mean. So when you have a flat, plate-like crystal, if it is landing on the major face on the plate, so it has enough, it is just landing on it, right? It doesn't fall off. So it works well. But when you make it stand, like so on the corner, then it doesn't work very well. So that's what we see. But I'm not sure like which factor is basically playing a role.
Okay, thank you.
Thank you, Sushil. Thank you. Sorry, Sushil, I didn't see you. Sorry.
No, it's okay. I didn't raise the Zoom hand.
Okay. I think we have well crossed the limit of 5:30, and I know Malla also has few meetings signed up in the next couple of hours. So we will relieve him right now, and I would like to thank all of you for participating in this wonderful colloquium. And it's a great start to our this year session. Malla, thank you for doing this, and we are exceptionally proud that you have published a fantastic paper from our country, and it's a very opened up a new science. So thank you, Malla. I would like to also tell the audience that next week we have another fantastic work that will be presented by Debojyoti Chakraborty, Dr. Debojyoti Chakraborty, who has come up with a paper strip method of detecting COVID-19, and this is done in IGIB in New Delhi, and this is also a fantastic work that will be discussed next week. So please tune in at 4 o'clock on the next Wednesday, which is 8th of September. So thank you, and I would like to thank the lecture theatre staff for putting the talk in lecture theatre as well. And with that, I conclude this colloquium. So again, I would have to thank Malla, and a big round of applause.
Thanks a lot. Thanks a lot.
I will stop.